Over the last 100 years, nuclear bombs have been a constant point of controversy. From protests of their destructive power to threats from foreign governments, the atom bomb has become an integral part of how we view modern history. But to fully understand just how large of an impact nuclear weapons can have, we must also understand how they work and where they come from. This all started in the early 1800s. Around this time, the prevailing theory was that everything in the world could be broken down into smaller and smaller pieces forever, while still remaining the same substance. But in 1803, an English chemist and schoolteacher named John Dalton proposed the idea that all matter was actually made of tiny, indivisible particles that looked more or less like a tiny ball. No one took much notice of Dalton's theory for nearly 100 years, until, in 1897, J.J. Thomson proved not only that atoms exist, but that there are even smaller particles within an atom. The negative electron was the first to be discovered, then the positive proton 20 years later. Finally, the neutral neutron was discovered in 1932. At its most basic, an atom is composed of two parts: a central nucleus, containing a jumble of protons and neutrons, and rings of electrons which circle around the nucleus. Around this time, a few scientists, including one Albert Einstein, began to theorize not only about what atoms are, but how they could affect the real world. These scientists realized that the everyday atoms our world is made of could be broken down into energy to create a far better fuel source than we've ever had before. But this story is not all sunshine and rainbows. This idea of the perfect energy source was blown out of the water when the Nazis invaded Poland in 1939, sparking the Second World War. In the top-secret Manhattan Project, the U.S. tested the first nuclear detonation, codenamed Trinity, in July of 1945, and dropped the first atomic bombs a month later on the Japanese cities of Hiroshima and Nagasaki. Since World War II, nuclear weapons thousands of times more powerful have been developed, but luckily never used against a human target again. But to better understand the risks that nuclear weapons hold, we must also understand how they work. There are two main types of nuclear reactions that power these bombs: fission and fusion. Let's start with fission. Fission is sort of like the little brother to fusion. Fission works by compressing the nuclei of already unstable elements together until they reach what is called critical mass, more commonly known as a very small ball. This hypercompressed state is usually created by surrounding the radioactive material with explosives and detonating them at the exact same time. When the material is squished together so tightly, nuclei begin to run into each other, creating energy and blasting neutrons around which will run into other nuclei. This process goes through the whole material in a very quick amount of time, creating what is called a chain reaction. This chain reaction creates an immense amount of energy by converting a small amount of matter into pure energy in accordance with Einstein's famous equation E=mc². When controlled, fission reactions can be used in nuclear reactors to produce electricity, but when uncontrolled can create devastating atomic blasts. The Hiroshima bomb used a fission detonation with a blast 15 kilotons in magnitude. To put that into perspective, a 15 kiloton explosion is equivalent to the detonation of about 15,000 tons of TNT. But fission bombs pale in comparison to their bigger brother, the fusion bomb. Fusion bombs also go by other names such as hydrogen bombs or thermonuclear bombs, but the way they work is the same. After the end of World War II, nuclear scientists were looking for ways to make bombs bigger and more powerful. They thought that if they could harness the power of nuclear fusion, they could create a bomb many times more powerful than using fission alone. Fusion is a process used on the sun to fuse together two atoms, usually hydrogen, into a singular helium atom while releasing a massive amount of energy. The only problem was that fusion requires extreme temperatures of around 100 million degrees Celsius. But lucky for them, they had just created the fission bomb, which was powerful enough to reach these insane temperatures. The most basic fusion bombs consist of two stages: the fission stage and the fusion stage. First, a fission reaction is triggered, which creates a massive fireball. Then, the heat from the fireball triggers a fusion reaction that unites together hydrogen atoms stored within the bomb, creating a second, larger fusion blast. The U.S. tested its first fusion bomb, nicknamed Ivy Mike, in 1952 with a blast of 10.4 megatons, or 10,400 kilotons, roughly 700 times more powerful than the Hiroshima bomb. The USSR were close on their heels with their own fusion bomb only a year later. Since these initial tests, fusion bombs many times more powerful have been created simply by adding more stages. Instead of a fission reaction that triggers a singular fusion reaction, they will use a fission reaction to trigger a fusion reaction, which then triggers an even larger fusion reaction, and so on. The largest nuclear bomb ever tested was the USSR's Tsar Bomba, detonated in October of 1961, with a blast of 50 megatons, over 3,000 times more powerful than the Hiroshima bomb. Lucky for us, nuclear tests are not nearly as common anymore. As the Cold War drew to a close in the late 1900s, big countries no longer saw the need for bigger and stronger bombs. In 1996, the Comprehensive Nuclear Test Ban Treaty was signed by many major countries, but this hasn't stopped others like Pakistan, India, and North Korea from continuing their tests. Like all history, if we forget the past, we are doomed to repeat it in the future. With countries like Russia and North Korea both threatening nuclear war, it is crucial that we understand how these weapons work when considering the magnitude of the destruction they can cause. Well, that's the end. I hate to start this channel off on such a serious note, but if you enjoyed the video, please consider hitting the like button to help this video reach more people. But that's it for this one. Till next time.